Welcome back once again to the second part of this video where we look at the trigonometric graphs. Okay, so we looked at sine and the cos graph, so now we've got to look at the tan graph. Alright, so the tan x graph, so y is equal to tan x. I said to you the tan graph is slightly different. Okay, first we'll figure out the tan values for a few angles from 0 to 360. So 0, 30, 60, I missed out 45. Never mind, I missed out 45. That's 90, 120, 135. Alright, so let's pick out 135. So tan 135 is in the second quadrant, so the angle that it makes to the horizontal is 45 degrees. So tan 135 would be equal to tan 45, but the only difference is that in the second quadrant tan's not positive, tan's negative. So tan 135 would be equal to the negative of tan 45. Tan 45 is 1, so tan 135 would be equal to a negative 1. Okay, let me pick out an angle in the third quadrant, or in the in the third quadrant. 210 again. 210 is in the third quadrant, and the angle it makes to the horizontal is 30 degrees. Alright, so tan 210 will be equal to tan 30, and there's no problem in terms of its sign, because in the third quadrant tan is positive. So therefore tan 30 is equal to tan 30 is equal to approximately 0.58, I think. Yeah, approximately 0.58. So therefore tan to 10 is equal to 0.58 as well. There is no difference in sign. Tan to 10 is 0.58. Okay, the rest of the values are on this table. Alright, but notice what the value for tan 90 is, and notice what the value for tan 270 is. I said infinity. Alright, why is it infinity? Alright, now let's look at this triangle. Okay, I made the opposite side purposely quite tall compared to the adjacent side to this angle here. Alright, so if I say the opposite side there is equal to 10 and the adjacent side here is 1, so tan theta of 10 by 1 is equal, tan theta is equal to 10. So that we got to find the tan inverse of 10, which would be equal to theta. So therefore theta is approximately equal to 84 degrees. Okay, so it's not quite 90 yet, but it's 84 degrees. Let me choose another triangle. Okay, this time I've made it even bigger, the length there, so I'll call that 20 and that 1. So again tan theta will be equal to 20, because 20 by 1 is still 20, and the tan inverse of 20 is 87 degrees. Okay, so we're approaching 90. Alright, so let me choose another triangle. I'll make this really tall, this opposite side, and the adjacent side really short. So this could be still a right angle triangle though. This could be something like, I don't know, 100 units, and this would be 1. So tan theta is equal to 100, and tan inverse of 100 would be 89.4. Okay, now if I continue to do this, make this really long compared to this, it would approach somewhere close to 90. Okay, so as the ratio between the opposite and the adjacent approaches infinity, it's almost 90 degrees. Okay, but you don't have a value for it, so you just end up saying that's infinity. Okay, same with this angle here, 270, because that fourth quadrant angle, the third quadrant angle, creates 90 degrees. Okay, so 270 is all the way here, so this angle is almost 90 degrees, and 90 degrees is same as infinity. Yeah, the tan value of 90 degrees is infinity. Alright, okay, now let's try and sketch this tan graph. Alright, Again, let me draw the axis and I'll then meet you in a minute. Okay, let's start plotting. Tan 0 is 0, tan 30 is approximately 0.58, tan 45 is 1, tan 60 is approximately 1.73, and tan 90 is infinity. Okay, now some of you would have done exponential graphs, not exponential graphs, reciprocal graphs in core 1 Edexcel syllabus. Okay, now reciprocal graphs look something like this. Okay, now if there's a point that approaches infinity, you draw that line using dotted lines. Okay, it never reaches infinity, okay, at a given point. So a graph like this would be y is equal to 1 over x minus 2. So at x is equal to 2, there's a line, okay, the asymptote is drawn. Okay, that dotted line is called the asymptote. Okay, by that what you mean is that at that point there is no definite value. Okay, even though it's technically infinity, there is no definite value, and all the points approaching that point are going to be stretched out in either direction, where it tries to get to that value but never quite gets there. Okay, so this bit here runs parallel to this line. Okay, so that's the same thing that's going to happen here. You're going to have an asymptote along 90 degrees. Okay, and if I were to sketch this graph, okay, and at 90 degrees you're going to have an asymptote, so it's going to look something like this. Okay, this isn't quite linear. I don't know why it's come linear. It should be nice and curvy. So yeah, so at 90 degrees is infinity. Wherever in maths, when you're trying to plot a graph, you have infinity involved. At that point you have to draw your asymptote and not quite, you know, reach infinity, but show as you get to that point, you are sort of reaching infinity, okay, along the asymptote line. Okay, now let's see what happens in the other direction. Okay, now if you try to figure out the tan value of something like tan 90.5 degrees or something like that, you'll get a very high negative value. Okay, so if you start out from tan 90.1 going up to tan 90.5, your negative values start decreasing. Okay, a tan 90.1 would have a very low negative value. Okay, so it's coming up from negative infinity. Okay, negative infinity. Alright, and then let me just redraw that. Okay, it's coming up from negative infinity. So if you take the value of tan 90.1, it will be a very high negative value. Alright, so at tan about 120, you're at minus 1.73, so somewhere here, and at 150 you're at minus 0.58, and at 135 you're at minus 1. So you probably look like this. Okay, alright, so that's from 90 to 180, and at 90 you're at an asymptote, so it's a similar sort of effect like what you have here on the exponential graph. Okay, okay, I've drawn the rest of the graph. Okay, so in the third quadrant the angles are positive, because in the third quadrant tan value of an angle is positive. Alright, where is that? Yep, third quadrant tan value of an angle is positive, and in the fourth quadrant the tan value of an angle is negative. See all these negative values for the angles in fourth quadrant. Okay, and you have another asymptote on 270, because at 270 the values approach infinity on either side. So you have an asymptote going up this way, reaching up to 270, and just as you pass 270, you have values sort of descending from infinity from the negative scale. Alright. Okay, now let's do a quick summary on all the three graphs that we've learned so far. So this is a sine graph. So from 0 to 360, it looks something like this, and the maximum value here for a sine graph is 1. Minimum value here for a sine graph is -1. The cos graph looks very similar to a sine graph, just that it's been shifted this way by 90 degrees. So it starts at 1, goes down to -1, comes back up to 1. Okay, and that's -1. Tan graph is completely different to these two. You have asymptotes, okay, at points where it approaches infinity. So you have an asymptote there, reaches 0, continues on to there. You have another asymptote there, okay, and that's a tan graph, and that's infinity. Actually, you don't usually show that on the graph. Okay, so this is your sine graph, sine x graph. This is your cos x graph, and this is your tan x graph. Alright, now let's see how you could transform these graphs. Okay, now you could very well draw sine x or cos x between 0 to 360. But what if someone asked you to draw y is equal to 2 sine x? How would this graph change if you were to draw 2 sine x? Okay, now let's look at that. Alright, now before doing this, you need to be very thorough with your transformations from core 1. Okay, transformations of functions. Okay, now if you had a graph f of x, alright, and this graph looks like this. Okay, 2 of x, what would 2 of x do to this graph? Okay, all the y coordinates would double. Okay, so 2 of x graph would look slightly stretched because all the y coordinates doubled. Alright, that's what happens when you transform it this way. Okay, when fx becomes 2 of x. Alright, what if I did a transformation like this? Fx was equal to this graph here. Okay, and if I want to do f2x, with that all the x coordinates halve. Okay, all the x coordinates halve. Alright, so the transform graph would look like this. If I halve this x coordinate, then it would be somewhere here. That point would still be the same because I can't halve 0, because half of 0 is still 0. And this graph would look something like this. Okay, because if I halve this, it'll be here, somewhere here. Okay, so all the x coordinates halve, whereas the transformation like this, all the y coordinates double. Alright, now using these principles, let's try and see what transformation has taken place for y is equal to sine x to become y is equal to 2 sine x. Okay, transformation that's taken place is that the entire function's been doubled by 2. Well, it's been doubled, yeah. So f of x has become 2fx. Now if this transformation is taking place, the y coordinates double. Alright, so if this was your sine x graph, all the y coordinates double, so your sine 2 sine x graph looks something like this. Okay, and the maximum and the minimum points will be +2 and -2. this is sine 2 sine x, and the y graph is just sine x. Alright, so you can see positive 1's doubled to positive 2, 0 can't double itself, everything, all the other points in between have doubled in value. Okay.